So you're tuning into this problem to watch me solve this, solve for the enthalpy for this combustion reaction of propane. And you may be looking at it saying, you know what, this problem looks awfully familiar. I think we've done it before. And if that's the case, you would be right. This is the exact same Hess's law problem that we looked at before. You might then say, why is it that you have it written on the board again? Why would we solve this problem again? And what I wanted to show you is that we have seen a method for solving Hess's law problem involving manipulation of these equations and their enthalpies to determine what the enthalpy of an unknown reaction is. Now I want to show you a different way that's a little more mathematical. Not mathematical in the sense that it is more complicated, because actually we're going to be doing the same mathematics we've done before, but we're going to do it in a slightly different way. And we're not going to have the need for any of these equations. We're only going to need the enthalpies. And the reason for that is because these are special enthalpies, because these are special chemical reactions. And what I mean by that is, if you notice, in each of these three chemical reactions, we have 1 mole of some product formed from elements that are in their elemental state. So here this has carbon and hydrogen in it, so C3H8 is formed from carbon and hydrogen in their elemental state. And here we have carbon dioxide formed from carbon and oxygen in their elemental state. And here we have water formed from hydrogen and oxygen in their elemental state. And in each of these cases, notice we form 1 mole of. And whenever we write the chemical equation like that, or we have a chemical equation written like that, the enthalpy of that reaction has a new name, and it's called heat of formation. And when we have heats of formation, we can go through the same process of Hess's law if we want to, and we can manipulate those, or we can use or do this problem a different way. And we can say, okay, we look at this reaction, we want to calculate its enthalpy. So the enthalpy of this reaction is going to be the sum of the number of moles times the heat of formation for the products, minus the sum of the number of moles times the heat of formation for the reactants. And I put reactants here inside the parentheses. It doesn't really matter. I'll just move the parentheses here. All right. Now that may look more complicated to you, but in reality, we know that this is the heat of formation for propane, and this is the heat of formation for carbon dioxide, and this is the heat of formation for water. And so this problem is going to be much simpler than what it seems. I'm just going to start working it because it makes more sense if we get started. So the heat of reaction, we're going to look first at the products. We've got our first product is carbon dioxide, and there are 3 of them. So that N for carbon dioxide is going to be 3. And we're going to multiply 3 times the heat of formation of carbon dioxide, which we know is minus 393.5 because we've already determined that's the heat of formation reaction. And you might say, well, do we always have to look and see from the equation whether there's a heat of formation? The answer is it's possible you might have to. But in reality, heats of formation are tabulated. They don't even write the chemical equation because we know that it's 1 mole of the compound formed from elements in their elemental state as the reactants. So we could write them if we wanted to. But in reality, in your book, there would just be a table of compounds and then whatever their heat of formation would be. So we'll just be able to find that number from a table generally instead of even having to have those chemical reactions. But notice we've got this symbol here, and that stands for the sum of. So that's summing up N times the heat of formation for all of the products. So we have this, and we're going to add to it the other product, which is our water. So in this case, we've got 4 the heat of formation of water is minus 285.8. And we're going to subtract from that the same thing, but for the reactants instead. What are our reactants? Propane and oxygen. So let's start with the propane. If we look at this reaction, we're looking at the combustion of 1 mole of propane. And so we have 1 times whatever the heat of formation for propane would be. So we find propane minus 103.85 kilojoules. And this is where it gets a little bit tricky, because we're going to add to it the oxygen. There are 5 moles of oxygen. So 5 times whatever the heat of formation for oxygen. And you might be saying to yourself, there is no oxygen in any, none of these reactions are for the heat of formation of oxygen. And the reason for that is that oxygen is an element in its elemental state. It's just oxygen. And elements in their elemental state have a heat of formation of 0. This trips up so many students. They'll get to the final exam and they'll say, you gave me all the heats of formation, or get to the exam and they'll say, you gave me all the heats of formation, but you didn't give me anything for oxygen. That's because you have to know that that heat of formation is 0 for oxygen. That trips up a lot of students. So at this point, it just becomes multiplication, addition, subtraction. So I'm not going to go through all of that, but I will tell you that if you work through this and report your answer to the correct number of significant figures, you should get minus 2,219.9 kilojoules, which should be the exact same answer that we got when we did the Hess's law way, where we rearrange these equations. And in reality, the math that we're doing is exactly the same. Students a lot of times are a bit more afraid of this way because they don't like to see all the symbols and they don't like the equation and these sigmas. They really throw them for a loop. But in reality, they're not really that scary. It just means adding up all those products for all of the different products. Notice how I use product and product in the same sentence. Product being the multiplication, so those two multiplied together. For all the products, we're going to add those all together. That's not really that difficult. And so, in reality, in my opinion, this way is much, much faster than having to do all the other manipulation and inspection. But to be honest, it doesn't really matter how you do it. There may be the case, though, where you are given a problem where you really have to work it this way as opposed to the other way with manipulation, because it's important that you understand how to use both variations of Hess's law for solving these problems.